In this lesson, I'm going to go over the problems that were in a midterm that I gave in the fall of 2015. These questions are pretty similar to the ones that you saw in your midterm, so if you feel like it, you could try working these out on your own, and then just watch the parts of the video that you need to get the answers correct. So in an article on cremations in early medieval Britain, H. Williams discussed the frequency of cremation burials found in 14 archaeological sites in eastern England. The data are given below. Find a 5-number summary for these data. So, the things in a 5-number summary, as in the 5 numbers that are there, are the minimum, the maximum, the median, and the quartiles, quartile 1 and quartile 3. And remember that quartile 1 and quartile 3 are the medians of the lower and upper half of the data. So the first thing that you have to do any of these things is reorder your data from either least to greatest or greatest to least. So smallest, we'll do smallest to biggest. So 14 numbers. The smallest number on the list is 34, then 35. Oh, it's like the next biggest one is 46. And there's 46 twice, actually, so list that twice. And then 51. And then 64. Then looks like 83, 86. 83, 86. Okay, then we have 119. 119 is next. 265. 385. 429. 523 and 2,484. And one way to do a quick check is to count and see that you have 14 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so we're probably good. All right, now the minimum is 34. The maximum is 2,484. Now to find the median, well, there are 14 numbers, so here's the first 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So there is no one single number that is the median, so you have to take the mean of the two middleist numbers. So 83 plus 86 over 2 gives us 84.5 for our median. Now here is the spot where people are going to mess up. Quartile 1 and quartile 3. So for quartile 1, you look at the lowest 7 numbers. And the thing that's funky here is you do include 83. So find the middle of that data. Well, that has a middle of 46. And for quartile 3, same procedure, but with these numbers. Well, the middle number there is 385. So you do use that 83 and 86. You do not use it if it's just like a number, as in if there had been one more number, say that 84 had been on there, then you would not use 84 in the Q3 and Q1 calculations. Okay, next. Identify any outliers. Explain how you arrived at your conclusion with numbers. So what we have for outliers are any numbers that are smaller than a certain thing, any numbers smaller than Q1 minus this 1.5 IQR, that's too small, or bigger than Q3 plus 1.5 IQR. That was our threshold for what qualified as an outlier. So the first thing we need to do here is find the IQR or interquartile range, which remember is Q3 minus Q1. So that's 385 minus 46, which is 339. 1.5 times that IQR gives us 508.5. And we're too low if below Q1, which was 46, minus 508.5. And obviously there are no negative burial sites, so there are none too low. We're too high if you're above Q3, which was 385, plus that 508.5, which gives us 893.5. And so thus, the only outlier we have is 2,484. But when I'm looking through your work, what I'll be looking for is, did you find this IQR? Did you do 1.5 times it? And did you find these numbers? That's what I'm looking at your explanation to be. Okay, give one example of each of the following variables. So a categorical variable. So this would be categories, no necessary ordering. As in, it's possible for this to have an ordering, but not necessary. So one thing here could be eye color. That could be a categorical variable. Another categorical variable that is ordered could be shoe size. An ordinal categorical variable is a categorical variable that has an order. So there, well, shoe size has an order, and you fall into a category. Another example could be a tax bracket. That's an ordinal categorical variable. A continuous quantitative variable. So continuous means that all sets of values in some interval are possible. So height is a good example of a continuous variable. Weight is another one. All right. The consumer advocacy group measures the achieved mileage for a random sample of 5 sedans of a certain make and model. The data are given below. And they might be trying to assess, like, does this sedan get the actual gas mileage that it claims it gets, which you could test using a t-test, actually, or finding a confidence interval, now that you know how to do those things. So first of all, what is n, the sample size? Well, there are 5 data points, so we have n equals 5. Find the sample mean x bar. So x bar will equal the sum of these divided by 5, which comes out to be 24 miles per gallon. So in our sample, the average MPG is 24. Calculate the sample standard deviation S. Round your answer to the nearest hundredth. So the sample standard deviation, remember, is this big old square root of the sums of the x's minus the mean squared divided by n minus 1. And I like to start finding the variance, which is s squared. And it's just that same thing except for not square rooted. Okay, and this is a little bit tedious, but you probably will have to do one of these calculations on your final. So this will be 28 minus 24 squared plus 21 minus 24 squared plus 24 minus 24 squared plus 25 minus 24 squared plus 22 minus 24 squared, all divided by 5 minus 1. Okay, so s squared, well, 28 minus 24 is 4. 4 squared is 16. 21 minus 24 is negative 3, but you square that and it becomes positive 9. Plus 0, plus 1, plus 4. All of that divided by 4. That gives us 30 over 4, which is the same thing as 15 divided by 2, or 7.5. So my variance is 7.5, and my sample standard deviation S is the square root of 7.5, which is approximately 2.74. And of course, you're allowed to use a calculator on your exam. I just didn't have one on me at this moment, so I had to subtract and square by hand. Another big idea in this unit was this empirical rule that says for bell-shaped data, 68% falls within plus or minus 1 standard deviation, 95% falls within plus or minus 2 standard deviations, and almost all the data, 9.7%, fall within plus or minus 3 standard deviations of the mean, that is. So we have a mean of 7 hours and a standard deviation of 1.5. So this is going to be 7 plus or minus 1 times 1.5. Well, 7 minus 1.5 is 5.5 on the low end and 8.5 on the high end. This will be 7 plus or minus 2 times 1.5, and 2 times 1.5 is 3. So 7 minus 3 is 4, up to 10. And this will be 7 plus or minus 3 standard deviations. Well, that's 3 times 1.5 is 4.5. 7 minus 4.5 is 2.5, up to 11.5. And this next question is an example of, using that just a little bit differently. So the verbal SAT score for students admitted to a university had a balanced distribution with a mean of 520 and a standard deviation of 40. What is the verbal SAT score such that only 16% of admitted students had a lower score? Well, you know that 68% fall within plus or minus 1 standard deviation. So that's 520 up to 560 down to 480. And the remaining 32% is half up here and half down there. And then what is the score so that only 16% of people are below you? Well, that is right here. So a score of 480 means only 16% are below 480. And then what is the verbal SAT score such that only 2.5% had a higher score? Well, same basic idea and picture, except for what you're thinking is that, oh, that's like half of 5%, which is 2 standard deviations. So there's 68%. There's 95%. Leaving 2.5% up top and 2.5% in the bottom. Let's figure out what those numbers are. This is 520, 560, 480, and then plus an additional 40, 600, and that number down there would be 440. So the score so that only 2.5% are higher, well, that's right here. This would be a score of 600. And one way to deal with normal data was to do something called standardize the data so that you look at things sort of in standard deviations. And then if you're 1 standard deviation away, you're in the middle 68%. 2 standard deviations away, within that you're within the middle 95%, etc. So here we go. According to the Statistical Report published by the U.S. Bureau of Prisons, the mean time served by the entire population of prisoners released from federal institutions for the first time is 16.3 months. we're going to assume the population standard deviation is 17.9 months. Martha Stewart was released from federal prison after serving a total of 6 months. Find the z-score for Martha's prison time. Remember that the z-score is equal to the observed value minus the mean divided by the standard deviation. So observed value of 6 months minus a mean of 16.3 divided by 17.9, that comes out to be negative 0.575 approximately. So interpret the value of Martha's z-score. For example, was the amount of time she spent in prison unusually high or low or not unusual at all? So because the z-score is negative, Martha spent less time in prison than the average prisoner. However, this is not unusually low. Because she's only 0.575 standard deviations below the mean. Or she's in the middle 68%. You don't become special until you're more than 2 standard deviations from the mean, is a good general rule of thumb. And what's a little bit deceitful here is you think, oh my gosh, 6 months is much less than 16.3, that must be unusual. But this large standard deviation makes that not very unusual. Another thing we had in this unit was how to find a sample size that produced a specific margin of error. And here we use that overestimate of margin of error, which was 1 over root n. And setting that equal to our desired margin of error, 0.04, we use some algebra, multiply the root n over, divide by the 0.04, and you get 25 equals root n. And then you square both sides, and we get 25 squared equals n. So n is 625. And what if your margin of error could be 15%, which is huge and unrealistic, but anywho, let's figure it out. So 1 equals 0.15 times root n, divide by 0.15, and we get 6.666 repeating, equals root n. Square both sides, we get n equals 44.444. And here, this is an instance where you actually have to always round up. So we'd have to have a sample size of 45. Because 44 would give us a margin of error that was too big. So you have to round up to the next nearest person. And you can't sample half a person. The Kelly Blue Book provides information on wholesale and retail prices of used cars. In the table below, there are age and price data for 10 randomly selected Corvettes between 1 and 6 years old. Note that X corresponds to the age of the car and Y corresponds to the price in thousands of dollars. Use the regression model to predict the resale price for a 3-year-old Corvette. So Y hat will equal 43.6 minus 2.8 times 3, which comes out to be 35.2, and this is thousands of dollars. So I'd like you to give your final answer in thousands of dollars, so dollars 35,200. The last observation was a 4-year-old Corvette that sold for $30,500. Find the residual for this observation. Well, remember that the residual is given by y minus y hat. We know that y is equal to 30.5 thousand. We just need to find y hat. So y hat is 43.6 minus 2.8 times 4, which works out to 32.4. So the residual y minus y hat is 30.5 minus 32.4, which comes out to be negative $1.9 thousand, or negative $1,900. So what that means is that this car sold for less than the average. Officially by $1,900. Okay, find the slope and describe what it means in this situation. Well, the slope is equal to negative 2.8. And remember that its units are units of y over units of x. So y is in the price, in thousands of dollars, and x is the years or age. So what this tells us is that the resale price of a Corvette decreases, because negative, by $2,800 each year. Find the intercept, and I mean the y-intercept of the regression model, and explain what it means. Well, this is the value of 43.6, and this is the price when x equals 0. And so this may or may not mean anything. I mean, you can argue this one actually either way, and I gave full credit as long as your answer made sense. This could mean that a new car it costs $43,600, or you could say it makes no sense as a new car doesn't have resale value. I mean, it just has the sale value. So that one I think really could go either way, but the obvious situations where this will not make sense is if you had, say, gotten a negative price for this car or something like that. So use this model to predict the value of a 20-year-old Corvette. Why is this unreasonable? Okay, well, we'll plug in 20. And you get something kind of crazy. You get negative 12.4 thousand. Well, so this is unreasonable because you're not going to pay somebody $12.4 thousand to take your old Corvette. That's what I would interpret negative money as. Suggest you would need to pay someone to take your Corvette. And the real reason is here we extrapolated too far outside the data. A study investigated the effect of aspirin on heart disease. A group of patients who were at risk for heart disease were randomly assigned to take either aspirin or a placebo. And at the end of the year, the number of patients suffering from heart disease was recorded in the following contingency table. So compute the following: the risk of having heart disease in the placebo group and the risk of having heart disease in the aspirin group. So in the placebo group, there were 25 with heart disease out of 100 total, so 0.25. In the aspirin group, there were 15 out of 150, which works out to be just a 10% risk. The relative risk of having heart disease in the placebo compared to the aspirin. So this is given by taking the relative risk for the first, so that's the placebo, divided by the risk for the aspirin, which comes out to be 2.5. So what this kind of is saying is the risk of heart disease is 2.5 times greater in the placebo group. Which sounds pretty profound, actually. And then the percent increase, remember this is given by relative risk minus 1 times 100%. So 2.5 minus 1 times 100%, which comes out to be 150%. So there was 150% increased risk of having heart disease if you took a placebo. And those kinds of things come up in like medical data all the time, so it's good to have some familiarity with what they mean and where they come from. In an ABC News poll, a random sample of 1,506 adults were asked, compared to buying things by mail order or in a store, do you think that buying things over the internet poses more of a threat to your personal privacy, less of a threat, or about the same? And of the people surveyed, 75% said this was more of a threat. So what is the margin of error of the poll? Round your answer to the nearest tenth. Well, the margin of error from what we learned in this chapter was 1 over root 1506, which was 1 over root n, actually, which is about 0.02577. If I want this as a percent, that will be 2.577%, which rounded to the nearest tenth is about 2.6%. And we use this margin of error to get a conservative 95% confidence interval. And this was given by your proportion, which was 75% plus or minus this margin of error. This will probably not be on the final because I'll have you find a confidence interval using the more refined methods you learned in chapter 10. But this was the basic idea we started with. And this gave us a confidence interval of 72.4% to 77.6%. This interval being conservative just means that it's wider than the interval you're going to get using the methods of chapter 10. Our study investigates the effect of aspirin on heart disease, so same thing. And we want to now do the chi-square statistic to determine if there's a significant association between aspirin usage and the incidence of heart disease. So let's start by finding the null and alternative hypotheses about the relationship between the two variables. So the null hypothesis is that there is no difference. There is no difference in heart disease rates. No difference in the rate of heart disease between these groups. HA is that there is a difference. back in this chapter, we found the expected values using a table. Now that we've been through the later chapters, we also know a shortcut formula, so let's just do this both ways. So remember that the expected values are found using row total times column total divided by total. Okay, so we have disease, no disease, placebo, aspirin. Okay. So for the first entry, row total 100, column total 40, divided by 250 works out to be a lovely whole number of 16. Next, row total of 100, column total of 210, divided by 250 also is a nice whole number of 84. For aspirin, we take 150 times 40 over 250, comes out to be 24, and here we do 150 times 210 over 250, which gives us 126. Now, if you are in a situation where you have to do this and you do have decimals, remember that you round them to 2 decimal places. Find the value of the chi-squared statistic. Well, the chi-squared statistic is given by the sum of the observed minus expected squared over expected. So in this case, that's 25 minus 16 squared over 16 plus 75 minus 84 squared over 84 plus 24 minus 15 squared over 15 plus 135 minus 126 squared over 126. That comes out to give you a chi-squared of approximately 10.045. Now, knowing what you know from the previous chapter, there's also this shortcut formula that tells you chi-squared is given by the total n, AD minus BC squared over C1, C2, R1, R2. So in this case, that would be 250 times 25 times 135 minus 75 times 15, all squared, all over 100 times 150 times 40 and times 210. And with this shortcut, there's no need for step B. So that's a nice little shortcut that you can use, and you should double check that it gives you the same value of chi-squared. The only instance in where it would be a little bit different is if you had to round in those expected values, you might get a little bit different chi-squared from the shortcut formula because it's more exact. Okay, can you reject the null hypothesis? Why or why not? Well, first of all, the degrees of freedom here is 1. And looking at our chi-squared table, we see that we have a chi-squared value of 7.88 and 10.83. So you know that the p is at the biggest 0.005. That comes from a chi-squared of 7.88. And at the smallest, it's 0.001. That comes from a chi-squared of 10.83. And probably it's closer to the one on the left because our chi-squared is close to 10. But this would be the p-value range. When you do this, make sure that your alligators eat the bigger numbers. And so this tells us that yes, we can reject H0 and accept HA. What this tells us is that the incidence of heart disease is different between these two groups. Okay. Alrighty, suppose you computed the correlation statistic R for both of the data sets pictured below. Which one is going to have a larger value of R? Why? So remember that R is between -1 and 1. So the mathematical way of saying that is -1 less than or equal to R less than or equal to 1. And the closer R is to ±1, the closer the points fall to the regression line. And think about this. Draw a regression line in for both of these data sets. I'll do it in a little bit dark colors. So there's an approximate line of best fit. Here's an approximate line of best fit. The closer those numbers fall to that line, the closer those numbers are to 1. So pretend I'd given you, say, I don't know, R equals 0.9 and R equals 0.6 as potential possibilities. You'd say, oh yeah, this one is 0.9 and that one's 0.6 because there's more spread in the second data. And which of those numbers is larger? The one that's larger is on the left. So there you go. So the school board of a certain community conducted an internet survey to assess residents' opinion about school funding policies. A simple random sample of email addresses of the 100 residents was obtained. These residents were emailed and asked to respond to the following question. Do you support increased funding for technology in public schools if it would reduce funding for fine art programs? Of the 55 people who responded to the email, 67% answered yes and 33% answered no. So what is the population of interest? Well, the population of interest is all residents of this, all voting residents. All voting residents of this community. And probably we'll say voting residents because they don't really care what the opinion of the children are. The sample was the N equal 100 people surveyed. So what type of bias is likely to be an issue with this sampling frame? Well, one obvious one is only 55 out of the 100 people responded. So this would be non-participation / response bias. And I kind of dislike question B because the sample could be the 100 people surveyed or it could be the 55 who answered. And honestly, I'm not 100% certain which one it should be. So I won't put any questions that are that ambiguous in the test. So a researcher investigating kidney stone formation examined 533 historical medical records of male patients that were randomly selected from 7 Chicago area hospitals. For each patient, the incidence of kidney stones was recorded, along with other information including weight gain, and age. So is this an observational study or an experiment? Now, this is an observational study. And the kicker with observational studies is that there was no treatment assigned to patients. When you assign a treatment to a patient, then you have an experiment. After analyzing the data, the researcher reported reaching the following conclusion. Rapid weight gain causes kidney stone formation in men. Is this conclusion appropriate? Why or why not? So you cannot conclude causality from an observational study. So this is no, it's not appropriate. As causality, or cause and effect, can only be concluded from experiments. And this was an observational study. It's best to say rapid weight gain is associated with a higher risk of kidney stone formation. That's all you can conclude, that there's a higher risk, not that it actually, one thing is causing the other. But these kinds of things might give you an idea of what kinds of stuff you want to study and what kind of experiments you want to do. So they can tell you where to go, but they cannot tell you cause and effect.